Hello, it's time to look at our note examples for day two. We're looking at synthesis reactions. So this is following the lab portion of synthesis reactions. The lab portion is meant to show you and allow you to observe how these reactions actually occur. Today we're just going to look at some examples so you can see what products may have actually been created out of those reactions. So let's start with metals and oxygen. Metals and oxygen definitely have a long history of reacting. Oh boy, we got a lot of them there. Let's start at the top. I don't know if we'll be able to fit phosphorus and oxygen down in the bottom there, but we'll start with iron and oxygen and take a look at that one. Okay, so just a little bit of background with these, the way they're written. We have at the top the beginnings of what we call a word equation, meaning that it's an equation written as words. So we have iron and oxygen, and then this spot here is meant to write out the rest of the word equation. The line below is there for drawing out or writing the formula equation as a balanced chemical reaction, okay? So that's the format of these. I know it's quite a lot to do, and we'll break it apart piece by piece so you can see what's going on. But that's typically what's going on. I like to personally write out the formula equation before I write out the word equation, the rest of the word equation, because the formula equation helps me figure out what's happening with the word equation, okay? So let's start with iron. So iron is Fe, and oxygen is O2. Okay, so what we're looking at here, again, remember this is synthesis reactions. We're looking at synthesizing or combining these together to make one thing. That would have to be iron oxide. It would have to be iron and oxygen being connected together as one compound. And that's what happens here, okay? But it gets complicated because iron on the ion sheet, this is a throwback, we have to use the ion sheet and the periodic table that we used way earlier in the year. Iron is a 2+ and oxide's a, iron is a 3+ in this case, and the oxygen is a 2-. So if these go together, we need to balance it out. We use the crisscross method, where the 2 would end up here and the 3 would end up there. So our combined compound would be Fe2O3. That does make it a little bit trickier to balance. We do need a balanced equation here because we have this 2 with the iron, and we previously didn't have that. We have a 3 with the oxygen, which doesn't balance either. The oxygens are the big hang up because we do need to make sure that they are equal. So 2 times this one gives me 6, 3 times the 2 over here gives me 6, but now my iron has 4. So we do need to come back and get the 4 on that side. And this here is just iron oxide. So that's how you finish your word equation by just writing down what you have for a product, which in this case is iron oxide. Okay, so that's a basic idea behind formula and word equations, and that's the basic idea behind synthesis reactions, where they make one product out of 2 or more reactants. Gold doesn't react, however. Okay, so gold, the reason we make jewelry out of gold is it's very non-reactive. There's oxygen all around us, you know, in the air that we breathe, in the water that we swim in, you know, there's oxygen available in all places. If your jewelry was made out of something that just reacted with that all willy-nilly, then it would not be a good thing. So this does not react. How do we indicate that? We have an abbreviation for this because it's actually a very common occurrence that something will not react. And we write NR. NR stands for no reaction. no reactions are still really important because they tell us the character of that reaction. So it isn't, something just to forget about here. It is important. I am writing the formula equation just to, have practice doing it. It's also good practice in a lab to write out what you did. We tried it. We didn't actually try it. Well, actually, I do, I guess, when I wash my hands. But gold plus oxygen is a no reaction. Okay. But what about hydrogen and oxygen? That definitely reacts. That reacts really quickly and fastly. If you remember when we did the hydrogen balloon, that's when we took hydrogen and oxygen, we combined them together. In a very, very loud way, they make water. Okay, let's look at how that works in the formula equation. So hydrogen and oxygen are both what we call molecular elements. They bond with themselves. They're more stable that way. So hydrogen is actually H2 and oxygen is O2. And then people might be wondering, well, wait a minute, why doesn't it make H2O2? Why doesn't it make, that would be hydrogen peroxide? It can't because the hydrogen peroxide's actually kind of a high energy molecule. You can't just kind of put hydrogen and oxygen together to make it. You have to have another process to make that happen. So we do have to balance this. And that you can see we have 2 oxygens, but they're not 2 over here. And that gives us 4 hydrogens, so we do have to come back and get 4 hydrogens that way. So that's the water being created. All right, now I left out number 5 from our examples here, just because I didn't have enough room for all of it. Carbon and oxygen will either make carbon dioxide or carbon monoxide. I'm going to do the carbon. Let's do the carbon monoxide. I think that's harder to balance. So this would actually be number 5, I think. Which one's the deficient one? Yeah, number 5 is the deficient one. We're changing it up. So if you don't have a lot of oxygen around and the carbon is combusting, then you're going to make carbon monoxide. So let's look at the formula equation first. Carbon is just C, and oxygen is O2. If you don't have a lot of oxygen around, though, then you're going to make CO. For number 4, you would have CO2, which balances itself like instantly, which is great. We have to balance ours. This is carbon monoxide. Hopefully you have carbon monoxide detectors in your house to make sure that you're not breathing this in accidentally, because it does, you can't smell it, you can't taste it, you can't see it, but it makes it so you don't metabolize oxygen, you basically suffocate. Not good. So we need 2 and 2. It's funny, growing up, we had a carbon monoxide detector in our house, and it went off at like 3 in the morning, and my dad got so annoyed with it, he threw it out the window. I'm like, Dad, isn't that like telling us that we should probably leave the house? Maybe we should go out the window, you know? All right, lastly, we have phosphorus plus oxygen. Phosphorus is very, very reactive. I'm not allowed to have it anymore. I got, it was on the naughty list. So, but in terms of this reaction, if we had some, it would definitely happen. And it's going to make phosphorus oxide, but not just phosphorus oxide. You're probably noticing that phosphorus is, oh wait, you can't actually, sorry. Yeah, phosphorus is a nonmetal. Okay, so how do we do that? Phosphorus being a nonmetal adds complexity to this whole problem, because usually we could look at the charges and we could crisscross them like we did with the iron. But here we can't do that because phosphorus is a nonmetal. Phosphorus being a nonmetal means that we kind of have to worry about the bonding structure. Ugh. Okay. So do we have room down here to do that? Not really. So let's just let me just tell you what it is. It's tetraphosphorus decoxide. Tetraphosphorus decoxide. Tetra meaning 4, and deca meaning 10. So the formula of this bad boy is actually P4O10. Okay. I don't have room to write the reaction down. Well, maybe I do. I don't know. The reason it's P4 is because phosphorus, if you remember from when we talked about molecular elements, is already P4. That's the way it is. Like hydrogen's H2, oxygen's O2. That's just the way they are. Phosphorus is P4. P4O10. So to balance this, you just need a 5 in front of your oxygen over here. And that would balance that reaction out nicely. So I know it's weird. It's one of those things you kind of just have to remember it. But we won't see that one ever again. So just kind of a weird case. Okay, so that's that's metals plus oxygen and nonmetals plus oxygen. All right, let's look at the next group, which is metallic oxides and water. So metallic oxides do in fact react with water pretty readily, and they make bases. Non-metal oxides and water make acids. Okay, so let's start with the bases first. So we have sodium hydroxide. Let's write that out. Sodium is an Na1 plus, and oxide is a 2 negative, O2 negative. So that's a Na2O, and this is plus water. I'm going to write water kind of weird to help us figure this out a little bit, although that might not help out that much. Water is a HOH or a H2O. It is fundamentally the same thing. I know it looks kind of weird that it has the, the hydrogen in front. It doesn't really matter too much, but what's going to happen with the metal oxide, though, is it's going to make a base. So what's a base? A base is a hydroxide, okay? So it has to have a hydroxide ion attached to it in order for it to be a base. So that's great. So that means for us, it's going to be an NaOH for it to be a base, which is sodium hydroxide. Okay, we'll balance that in a second. Let's look at barium oxide. Barium oxide is a BaO. Water is a HOH. The reason this is a BaO is barium actually does have a 2 plus charge, and the hydroxide is a 2 negative charge. So, they balance each other out. But after the formula, after the reaction, that's going to be a BaOH2. It needs 2 hydroxides to balance out the 2 plus of the barium. So it's got parentheses around it. But that is barium hydroxide. And they both do react in that way. All right, so we do have to balance these, but I wanted to just write the formulas out so we could compare them a bit. So sodium oxide and water makes sodium hydroxide. Barium oxide and water makes barium hydroxide. Hydroxides are bases. Metal oxides and waters reacting with water creates a base. All right, so here we have Na, but before we had two NAs. So we do want to balance that by putting a 2 in front. And that does give us 2 of the hydrogens and 2 of the oxygens. If you look back, we do have oxygen here and here. So that's 2, and we have 2 hydrogens in the water. So that equation is balanced like that. And this one actually balances itself automatically because this 2 distributes. So we have 2 hydrogens and 2 oxygens, which we have 2 hydrogens and 2 oxygens on this side. So that one balances itself out automatically. Okay? So metal oxides and water create a base, but non-metal oxides and water create acids. So let's look at these 2 examples. So we have sulfur, sulfur dioxide. You'll notice that the formula does have to tell us, with a nonmetal oxide, it has to tell you how many oxygens there are. So it's telling us here that we have a dioxide. There's 2 oxygens. And down here, it's telling us both how many nitrogens we have and how many oxygens we have, okay? So we have dinitrogen, which is N2, penta, or pentoxide, which is 5, N2O5. And these are both plus water. I'm writing them as, again, HOH, just to be annoying, but it helps me visualize what's going on in the case of these reactions, okay? So what are these going to make out of the reaction? Well, the acids have to start with a hydrogen, okay? And in the case of the sulfur dioxide, we don't have 1 hydrogen, we actually have 2. And it all gets kind of smushed together, okay? So I know this is weird, but we end up with a H2SO4. The reason, SO3, sorry, SO3, because there's only 3 oxygens. Okay, H2SO3. This is an acid because it does start with a H. And it would donate that H in solution and cause all kinds of problems, okay? Now, that one was kind of simple because it all gets kind of smushed together. But what usually happens is it makes something that you have to balance, you know, like it doesn't come out. This one, excuse me, balanced itself. This one does not. This one makes nitric acid, which is HNO3. HNO3 is nitric acid, and you can see that it is not balanced, right? Like we have the 3 oxygens, we had 6 before, we had 1 nitrogen here, we had 2 before, we have 1 hydrogen here, we had 2 before, but it's not hard to balance. As you can see, everything just really needs to be doubled. So in this one, in number 9, it all came out perfectly and we didn't have to balance it. In number 10, all we had to do was put a 2 in front of the nitric acid. So balancing is not really ever that hard with these reactions, but it's hard to write the equation out, right? So now let's name these. So this is sulfurous acid. Which I know sounds weird. We didn't cover naming acids, so that one's just kind of an odd one, and that is the one that was created in the lab portion of this, of synthesis reactions. And this one, as I mentioned, is nitric acid. Oh, there's an O in there somewhere. Sulfurous. Sulfurous acid, sorry, and nitric acid. Nitric acid doesn't seem like it, but it actually is a pretty common acid. Sulfurous is not. We have sulfuric, you should know sulfuric, you should know hydrochloric, and nitric acid is nice to know as well. So anyway, those are the notes and examples for synthesis or combination reactions. We're going to skip over combustion reactions, and later we're going to look at decomposition and single replacement reactions, and that will be all of Unit 7 for us. Write these all down in your notes. It's good practice. The only ones that you have to do for homework are the ones from the lab part. Use these examples that I've provided for you to help write out those reactions and get a good handle on what's going on with those. And I'll be giving you an answer key later to help show what those reactions actually create so you can check your work. All right, thanks and have a good day.